Welcome, I am Lavinia and today I will be talking to you about my PhD research on the switching kinetics of tungsten-doped vanadium dioxide powders. The outline of my presentation is the following. Firstly, why is there a need for smart windows and how they work? Then, why vanadium dioxide is an advantageous material and its challenges. Later, how these challenges are resolved, and then the kinetic study of the powders. Lastly, the conclusion with the future works. The problem is that there is an increase in the world's energy needs and demand. In fact, buildings account for 30 to 40% of the world's total energy consumption. This means that a lot of energy is used for heating and air conditioning in buildings. Therefore, there is a main driving force to increase energy efficiency and, most importantly, to decrease energy losses. Additionally, the use of glass in construction has increased greatly over the years. For example, many of you probably recognize this building. This is the City Hall of Maastricht. On the other hand, this is the City Hall in Hasselt. You can see there's a great change in construction over the years. The amount and the size of windows has increased greatly. This is because glass is very lightweight and allows natural light into the building, but the main disadvantage is that a lot of heat is lost in winter and a lot is gained in summer. Therefore, the current problem is that the glass window allows too much heat gain, especially during the summer, leading to the inner temperature to increase, just like greenhouses. So, the solution is to regulate the heat gain of the window through the addition of a thermochromic coating onto the glass. With the addition of this coating, the inner temperature will be lower because of the infrared light being blocked. This will reduce the need of air conditioning. The question now is, how does the thermochromic window actually work? Firstly, the thermochromic coating is needed. This coating changes its optical properties with temperature. This change specifically occurs at the critical temperature. The coating is made of vanadium dioxide, which when applied to a window on a cold day, it will allow the infrared light to enter the building. While on a hot day, when the coating temperature is above the critical temperature, the infrared light will be absorbed and reflected out of the building, reducing the energy entering the building. More specifically, the vanadium dioxide structure has 6 polymorphs. The most important is the monoclinic vanadium dioxide, as this is the structure that changes to tetragonal when heated. The structural phase transition is reversible and is referred to as the metal-to-insulator transition. Due to the tilt in the z-axis, the material changes from being semiconductive to metallic, which means it becomes infrared light reflecting. There are various challenges in the application of VO2 to windows. One of the main ones is the relatively high switching temperature of around 68 degrees, which is not ideal for a smart window. This can be resolved, though, through doping of the structure with different elements. The second challenge is that the luminous transmittance is low. This means that the coating is not completely transparent and has a tint and is undesirable for windows. This can be approached through decreasing the particle size, or by stacking of the particles, or by encapsulating air. This is all to avoid light scattering. Differential scanning calorimetry is one of the most important and most used characterization techniques for vanadium dioxide powders. DSC is a thermal analysis technique which measures the difference in the amount of heat required to increase the temperature of the sample with respect to a reference. When VO2 is heated, an endothermic peak is visible as energy is absorbed to change the structure from monoclinic to tetragonal. On the other hand, when the material is cooled down, energy is released, therefore resulting in an exothermic peak. The peak temperatures are often used to indicate the critical switching temperature of the material. As you can see, for the heating step, it is around 68 degrees. Additionally, a very important parameter is the area under the exothermic and endothermic peaks. This results in the enthalpy and can be used to evaluate the purity of the material, as the theoretical maximum is 55 joules per gram. The switching temperature challenge has been addressed through the addition of tungsten to the crystal structure. This is done during a synthesis by mixing the vanadium liquid precursor with the tungsten liquid precursor in different quantities to achieve from 1 to 3.5 atom tungsten percent. With the addition of the tungsten in the DSC, it is possible to see the decrease in the peak temperature. The peaks are broadening and also multiple peaks appear, which indicates different phases being present. The addition of tungsten decreases the temperature linearly, and therefore it can be tailored very accurately. For window application, it is desired to have a temperature between 15 and 25 degrees. Therefore, it is desired to have an atom percent of tungsten between 1 and 2%. Using the DSC, a kinetic study was carried out of the phase transition of undoped VO2 and doped VO2. To do this, 4 heating rates are used to look at the conversion, which is also called alpha. This is the conversion of VO2 from monoclinic to tetragonal. The image on the left illustrates the DSC measurement with the 4 heating rates. The peak area with respect to time corresponds to the running integral of the peak. This is the conversion of VO2 from monoclinic to tetragonal. Therefore, below 60 degrees, when VO2 is monoclinic, the conversion is 0, while above 80 degrees, this value is 1. For the kinetic study, the gradient at the 50% conversion is very important, as this gives the rate of conversion of the VO2 monoclinic to tetragonal. Additionally, the corresponding temperature when alpha is 0.5 is also required. Using the information from the previous slide, we can now look into the principal equations needed for the kinetic study. Firstly, the single-step kinetic equation, which is based on the well-known Arrhenius equation, is used. Applying isoconversional principle that the reaction rate only depends on temperature when the extent of the conversion is constant leads to the second equation. Then, rearranging the first equation leads to the basis of the Friedmann isoconversional method. For the detailed explanation, please refer to our recent publication. This equation is used to derive the Friedmann plot, in which the conversion rate is used and the corresponding temperature at this rate. The gradient of the Friedmann plot results in the activation energy for the structural phase transition. So now combining all the previous equations and the running interval of the vanadium dioxide at various heating rates results in the Friedmann plot, which is illustrated here on the right. We can see that the plots are almost symmetric, and also they are non-linear. The non-linearity is just the fact that activation energy is affected by temperature. Additionally, combining all the Friedmann plots for the doped VO2 results in a very similar activation energy, which range between 130 to 560 kilojoules per mole. This value depends on temperature. So it also makes it a bit difficult to compare the values. The similarity in the plots also suggests that the doping does not affect the kinetics of the structural phase transition. Moving on to the second challenge previously mentioned, the particle size is decreased through wet bead milling of commercial VO2. The VO2 is dispersed in isopropanol with a weight content of 10 weight percent in order to have enough interactions with the beads within the chamber. Cooling water is required to make sure the temperature remains below 35 degrees to avoid evaporation of isopropanol and also to avoid oxidation of vanadium dioxide. Nitrogen flow is applied in the mixing tank. But there are many different parameters which actually can be changed during the milling, and mainly the pump capacity and the rotation of the rotor are increased during milling. If we look at the SEM images of different samples taken every 3,000 kilowatt hours per ton, we can see that the particle size it decreases from about 5 microns, to nanoparticle size between 100 and 150 nanometers. The preliminary results of the bead milling of the vanadium dioxide are the following. Firstly, the DC peak intensity decreases and broadens, which leads to a decrease in the enthalpy of the vanadium dioxide. Additionally, the peak temperature is increasing for the heating step and the decreasing for the cooling step, making the region of the structural phase transition much larger. Additionally, the overall enthalpy decreases from 84 joules per gram to 30 joules per gram, while the particle size decreases from above micron to around 129 nanometers. To conclude, the smart windows have a great potential in decreasing the energy consumption of buildings. The main challenges are the high transition temperature and the luminous transmittance, which is low. These are both addressed. The first one is addressed through tungsten doping, and then a kinetic study was also carried out. From this study, we also found that the results are that the symmetric behavior suggests that the mechanism between both the structural phase transition is similar. The nonlinear relationship is because of the activation energy being temperature dependent. And lastly, doping does not seem to change the kinetics. Additionally, the bead milling was effective to decrease the particle size from the micron size to nanoparticles. Then for the future works, we would like to work on the powders to carry out the kinetic study on the change in the particle size. Further characterization of these powders are required. Then coatings would be required to be made. And these coatings, the nanoparticles would have to be implemented into the films and then investigated the properties of these particles within the films and how they can be optimized to gain the best performing glass windows. And lastly, look into the scale up for the production of coated glass windows. I would like to thank you all for listening and thank you for the contributors in Hasselt University and Brightlands Materials Center and all the partners of our research. Thank you very much.